Hello, my name is Daniela Diaz Caballero, and for this video, we'll be discussing Physics 2212 Lab 5, Magnetic Braking with Faraday. During this video, we'll give a brief introduction to the experiment, which will include the purpose of the lab, any assumptions that were made, and the results that were discovered. Last but not least, I will conclude by discussing theoretical questions that can be inferred by our findings of the experiment. The purpose of this experiment is to collect observational data of the magnet falling through a conductive tube of aluminum foil, model the magnet interaction computation, and compare the computation predictions with the observed data. The fundamental principles we covered during this lab were Faraday's law in order to help us find the quantitative relationship between the magnitude of a non-coulomb electric and the rate of change of the magnetic field. We also used Lenz's rule to get a non-coulomb electric field to drive current in the directions that would make the magnetic field that attempts to make the flux constant. The result was that the experimental data took 1.67 seconds and the model data took 1.478 seconds. Before going to the calculations, let's discuss the pre-lab instructions and expectations. For lab 5, we were to observe when a powerful magnet is dropped straight down a conductive tube and falls out the other end. From there, we were meant to calculate the time it takes the magnet to fall through the length of the tube. To do this, we start by using a magnetometer app to determine which end is north. Then we hold the tube vertically and position the magnet just above the top open. From there, we drop the magnet through the tube and record the time when the magnet enters and exits the tube. For this lab, the materials needed were a smartphone, bar magnet, roll of aluminum foil, and a ruler. Now moving into our data collected from the experiment. Here we can see that the mass of our bar is 0.023 kilograms. The magnitude of the magnetic dipole moment is 2.5445 amps meters squared, which was calculated in lab 3. The length of the tube was 0.27 meters, width of the tube was 0.01 meters, and radius of tube was 0.019 meters. From there, we ran our experiment, and we found that our average time was 1.67 seconds for the magnet to enter and leave the tube. Now continue with the computation model. The creation of this model is separated into a couple of steps. Step 1, I enter my measurements into the code and use those values to create a visualization of the bar magnet. Step 2, I created a function for the magnetic field at a certain location using the bias-Savart law. Step 3, I created a function for the changing flux through time. Step 4, I added a line to calculate the current in the wire, which equals a change in flux over resistance. Step 5 and 6 calculates the magnetic field of each ring. Step 7, I calculated the magnetic force on the magnet using the gravitation constant and mass of the magnet. Step 8, I updated the magnet's position and velocity using Newton's second law. Here, we can see the output of the computation model. According to the model, the time in the tube is 1.478 seconds. Now we're going to take a moment and interpret the simulations that we just did. In our first observation, we can tell that the red represents clockwise while blue represents counterclockwise. We can tell due to the fact that there is a downward increase in the changing flux. This means that the induced current ends up flowing counterclockwise. So in our second observation, if the magnet is flipped around, the forces that act on the magnet and the total time in the tube would remain the same, but the current would end up flowing in the opposite direction. For our third observation, in a real-world system, the total time in the tube would end up being longer than the one calculated by the computational system. The computational system could become more accurate if we were to take into consideration air resistance. Last but not least, our fourth observation, the shape of velocity versus plot tells us that the velocity immediately decreases, then goes up a little before plateauing for a period of time and ends up decreasing again. This plateau means that the bar magnet is not accelerating, which indicates that the gravitational and magnetic forces are balanced in the tube during this period. Last but not least, we're going to be discussing theoretical questions that we can infer based on what we learned in this experiment. In the first question, is the following. What is the resistivity of the conductor where reduced as close as possible to 0? Then this would end up making that the induced current would end up being increasing, and therefore the magnetic force would increase as well. This means that the magnet would end up falling slower. For our second question, if there were holes or slots in the tube, the resistance would end up increasing due to the fact that there are less complete rings, and therefore this would decrease the induced current and the magnetic force. Unlike the first question, this would result in the magnet ended up falling faster. Last but not least, our conclusion. Based on this experiment, the experimental system takes longer than the computational system, given that the results were that the experimental system took 1.67 seconds and the model data took 1.47 seconds. Thank you for watching, and please do not hesitate to reach out if you have any questions.